So in this video we will learn about inverse functions. Before that we have to have one extra definition in order then to fully define our inverse functions and what they are. And if you remember, first of all, that a function was defined as that for every x value, for every input value, there's only one output value, only one y value. So now we define today a function to be one-to-one when for every y value there's also only one x value. So for every output there's also only one input. And as we had the vertical line test for finding out when a function is a function, we can use the horizontal line test in order to find out whether a function is one-to-one. If a function hits anywhere the horizontal line twice, then it will not be one-to-one. So now, equipped with that, we can now say that a function must be one-to-one in order to have an inverse, because the inverse function of a function f reverses the process of the original function. So that means the input and the output switch roles. So what before was the input is now the output, and what was before the output will now be the input. And we can only do that if we have clarity that the pair belongs together. So one input, one output, and vice versa, else this will not be possible. So now, if our original function is given as f of x, or how we often write it, y, our output equals f of x, then we define the inverse function the following. We can say x is now the inverse of y. That means if we apply our inverse function onto our outcome, then it will deliver us the input. Now if we have any variables other than x and y, if we for instance have the temperature and time, so we are tracking the temperature outside over several days, then that would be it. So our inverse function would now produce the other variable. However, if our variables are x and y, we are so used to graphing x on the horizontal axis and y on the vertical axis that we will actually switch our variables so that we can still graph y on the vertical axis and x on the horizontal axis. So therefore we will be still writing y equals, because that's what we are used to, and then we take our inverse function and we apply it on x. However, the function will look different. It will be the inverse function, and so we right away in a second go through an example that hopefully makes that clear. We will actually switch x and y, but then we will solve again for y in order to then be able to graph. And so that is written out here. So to find our inverse, we switch the variables x and y, and so for y at the end. Now as you have noticed, our inverse function is written as f and with a -1 in the upper right corner. So there's potentially a temptation to read it as f to the power of -1 and treat it as such, but that is not the case. So that little -1 in the top right corner means that this is the inverse function. And it comes from that basically division is the inverse of multiplication, but we are focusing for this notation on the inverse. It does not mean, so that's that last sentence here in the box, that does not mean that it's 1 over f of x. So that's a very big thing to remember. It is not that. So let's go ahead and look at an example and see how this all looks in action. So we're starting with a function f of x equals 3x plus 2. So you hopefully recognize that right away as a line. And a line is one-to-one, and therefore it has an inverse, and it is now on us to find that inverse. So let's start by rewriting our original function by writing it as y equals, instead of f of x, we know that we are dealing with function f, so we just write y equals 3x plus 2. And now the first step will always be, in order to find our inverse, to simply switch x and y. To simply switch x and y. Now, in order to then be able to graph it again, we will now solve for y. So I'm going to rewrite the same equation and give it a little bit more space, because my first step will be to minus 2 on both sides, and then I get x minus 2 equals 3y. And then my last step is to divide by 3 on both sides. So I get on the left side x minus 2 divided by 3, and on the right side I'm left with y. So therefore my inverse function I can write as f inverse of x equals x minus 2 divided by 3. I can also, if I want to see a little easier my slope and my y-intercept, I can simply write that as 1/3 x minus 2 over 3. So we now have our inverse function, and the next thing we are going to do is actually graph both of our functions. So our first function is our original function f of x, and that is 3x plus 2. So I'm going up 2 steps for my y-intercept, and then 1, 2, 3 up and over 1 lets me end up here, and then I go the other direction and I get some points here and here, and I can now draw my line, and I'm going to label it with f of x. And now I'm going to draw my inverse function in the same coordinate system and see what I get. So here now my y-intercept is minus 2/3, so I have to kind of estimate that a little bit. And then our slope still going up, at this time only 1 and then over 3. So I come here to this step and I go 1 up and 3 over, and then a few more in both directions. And I'm going to connect my dots. That came out actually quite perfectly. There we go. And again, I'm going to label my function here with f inverse of x. Now before we move to the last step, I would like to take a look at our graph. It looks like they have some kind of symmetry to them, and so I'm going to draw a line between them, which is right in the middle between them. And when I now look at that line, then I see that the equation of that line is y equals x, because it goes through the origin and then has a slope of 1 up over 1. That is characteristic for inverse functions. So the original function and its inverse function, when we draw both of them in one coordinate system, they will be mirror images always over the line y equals x. Now we can also use our newly found composite functions to show how that also comes out algebraically. So we are going to do a check like we are asked to do. So we are asked here to find f of f inverse of x, and then afterwards f inverse of f of x. And so the proposition is that that comes out to be x. Let's see what happens when we do that. So this will be our check. And for the first check, we find f composed with f inverse. So f of f inverse of x. That means my inner function is going to be x minus 2 over 3. And then we plug that now in as our x for our outer function, which is our original function. So I get 3 times, and instead of x, I write my output from the other function, x minus 2 over 3, and then at the end I have plus 2. So what happens is that we can cancel our two 3's, because it's 3 divided by 3, and so we are left with x minus 2 plus 2. Well, they cancel out as well, so we are left with at the end with x. That means if I input my inverse function output into my original function, I get my original input x back as the output, which is exactly signified by that it is mirrored over the axis y equals x. So let's show it in the other direction, f inverse of f of x, it's the other way around, and see if that also comes out correctly. So that would be f inverse of my original function being 3x plus 2. Now in my f inverse is x minus 2 over 3, except my x minus 2 is now 3x plus 2. Then I write my minus 2, and at the end over 3. Well, plus 2 minus 2 cancels out, so I'm left with 3x over 3. And now the 3's cancel out, and I'm again left with x. So if I look at my original function f of x, and I'm going to identify here, for instance, the point 1, 5, I then have a similar point on my inverse function, which is over here, that is 5, 1. So they correspond to each other, and so when I plug in my original x of 1 into my original function, I get 5, and I take that 5 and go to my inverse function, voila, I get now 1 as an output. So that is how it is shown, that it is mirrored over the y equals x axis, and that is always a great way to check if you have the correct inverse function.